A very good morning, all. Welcome to AICTE-ISTE sponsored Induction or Refresher Online FDP on research methodology, tools and techniques, Day 6, Session 7. And today's resource person is Dr. S. Chowdhury, AI Specialist, IBM USA. Let me take an privileged opportunity to introduce our resource person, Dr. S. Chowdhury. Dr. Cherukuri Sadashiva Chowdhury is an AI specialist with IBM. Dr. Chowdhury is a multifaceted computer scientist with an application-oriented research background and experience in multiple areas of computer science, including artificial intelligence, multimedia processing, retrieval, high-performance computing, hardware design, and development. His experience also spans across multiple industries, verticals including quantitative finance, oil and gas, medical devices, and US government. Dr. Chowdhury obtained his doctorate degree in computer science and engineering from the University of South Carolina, USA. His research work has led to several publications in reputed journals and conferences in the field of computing. He received multi-million dollars in funding from US government agencies for his application-oriented research proposals. Dr. Chowdhury's current efforts at IBM involve evangelizing AI adoption in enterprises and cross-disciplinary academia, conducting training programs on foundations of machine learning, designing AI solutions, and optimizing the compute performance of machine learning workloads. A hearty welcome, sir. Thank you so much for accepting our invitation.
Thank you, Radhika. Thank you. It's my pleasure to be with you all today.
Thank you, sir.
Can I go ahead and share my screen?
Yes,
I want to
sir.
share some slides
Yes,
with
sir.
you.
Yes, sir.
Sure. So I have a question. There are about 30 participants. So do we have mostly faculty members or do we have students? What is the audience
All are
like?
faculty members only, sir.
Okay. All right. Thanks. Okay. Do you see my screen now?
Yes, sir.
Okay.
It's visible.
All right. Good morning, all. Thank you. Thanks for the generous introduction. And it's my pleasure to be with you all and to share my knowledge in AI and machine learning today. So the title of the talk, Machine Learning for Academic Research. There is a lot going on in AI, and AI is being used by several disciplines across academia. And my goal today here is to introduce you to AI, fundamentals of AI, and give you a glimpse of how we all can leverage AI. I mean, you don't have to be a cutting edge researcher in machine learning in computer science department at IIT or MIT to be able to use machine learning. Everybody can use machine learning these days for their teaching and research. So my goal here is to convince you, to motivate you to use AI for your teaching and research. I have some introductory slides, and I would rather make it interactive session. I have a few slides. I have about 30 slides. I'm in no hurry to go through all these slides. It would be better if it is a question answer session. I will use these slides to go through, to have a flow, to give you some storyline. I will use it as a storyline, but please feel free to stop me and ask questions at any point. So what's AI? Let's ask this fundamental question. What is AI? What is machine learning? What is deep learning? I mean, these terms could be overwhelming and confusing for a novice engineer if you're not specialized in AI or if you're not in computer science. So what's AI? What do we mean by artificial intelligence? So the computers by themselves are intelligent devices, right? They can do pretty good calculations. They can do arithmetic at blazing speed, and they can process tons of information. So they are already intelligent devices. Then what do we mean by artificial intelligence? And why do we need to study this as a separate field within computer science? Well, we want computers to be more intelligent. We want them to behave like us, somewhat like us. Without artificial intelligence, the computers become mere calculation devices and information processing devices. Instead, we want to take it a step forward and make them think like us and behave like us. Broadly speaking, that's what artificial intelligence is about, making them more intelligent. Now, Alan Turing, if some of you are in computer science, Alan Turing is the father of computing, and he has set the boundaries of computation about 70 years ago during the Second World War time, right? When Turing machine was invented by Alan Turing. So he has set the boundaries of computation, and we are still within those boundaries of computation. He has clearly examined and established the problems that the computers can solve and the problems that the computers cannot solve. So is AI within those boundaries? Of course, definitely. It is just within those boundaries. We just have a bunch of algorithms and some programming paradigms that constitute AI, but it is all going to be on the same Turing machine. Now, within those boundaries of computation, how do we make them more intelligent? Right? How do we make the computers more intelligent? Well, we can try to make them mimic the behavior of human brain. Right? That's one approach. Brain is proof by example of intelligent behavior. So we can try to make the computers behave like brain. And that's what neural networks initially tried to do. But we cannot take that too far. And there are a couple of reasons for that. First thing is we don't understand brain. We have no idea how the brain functions. The so-called neural networks are in fact a vulgarization of the human brain. It just mimics the structure of a human brain as far as we know about human brain. So we cannot understand brain completely, and we don't even know a fraction of how brain functions and how this human intelligence came into existence. Now, the second reason for not fully trying to mimic the brain is researchers, when they tried to mimic the brain, they couldn't get better performance in machine learning. So modern AI and modern machine learning is not about mimicking the brain or trying to imitate the human brain, but it is about solving practical engineering problems, getting inspiration from these mathematical fields that we know, like probability, optimization, etc., linear algebra, and discrete mathematics, um, optimization algorithms. So the machine learning and artificial intelligence tries to get inspiration from all these various fields and tries to solve practical engineering problems. That's what AI is about. It's not about understanding human brain or mimicking human brain. Now, there is a different field called computational neuroscience, which tries to understand human brain at a more fundamental level. And that's a different field from in computer science. That is a different field from artificial intelligence. All right. So we talked about AI. We talked about artificial intelligence. Now, what is machine learning? Let's take this a little bit further. I mean, if you're finding it too basic, or if you're finding it, if you want to get into glory details of where machine learning is used in academia, please let me know, and I'll be happy to. I can go on for a couple of hours, but you will have to tell me what what is interesting to you. Now, what is the difference between machine learning and artificial intelligence? What do we mean by machine learning? So we want to make these computers intelligent, and people have tried out different methods. Initially, the field of artificial intelligence focused on problems that are difficult for human beings, like playing chess. It is hard to play chess, right? And it is hard to beat Gary Kasparov, who is a grandmaster in playing chess. So initially, researchers in computer science and researchers in artificial intelligence tried to solve those problems. How do we make computers play chess? And I think you are all familiar nowadays, the computers have become pretty good at playing chess. In fact, it was in year 1997 that IBM's Deep Blue system has defeated Gary Kasparov in chess. So the computers were able to beat the grandmaster in chess, right? So it's a solved problem. Playing chess, developing algorithms that play chess is a solved problem. It's a great accomplishment. It's a huge accomplishment. But it turns out that chess is a very controlled environment. We have about 64 squares, right, and 32 pieces on each side. Sorry, 8, 8, 16, 32 pieces on both sides, 16 pieces on each side, and we have 64 squares. And there are valid moves and there are invalid moves. So it is possible to create a gigantic graph that can enumerate all the possible steps in the game of a chess. Well, we cannot go all the way to the end of the tree because the number of possible steps are huge, but it is possible to build the tree to a certain extent, and then we introduce some heuristics, and we can play a pretty good game. The algorithm can be pretty good, can become very good at playing chess just by going through the tree, just by going through different paths in the tree. It's a rule-based system. So what is a rule-based system? Everything that we do, the conventional programming that we are doing is rule-based programming. We just give a sequence of instructions for a computer and it just blindly executes them. So the rule-based systems are not able to solve the real AI problems. And playing chess is hard for human beings, but it is pretty easy for computers. Now, recognizing an image, looking at an image and saying whether it is a cat or a dog is very easy for even a 4-year-old kid, but it turns out to be a very difficult problem for computers. Why is that? Well, there are infinite number of possibilities. There are various kinds of cats. Cats come in all shapes, all colors, right? There are hybrids. There are all kinds, and the background, the possibilities for the background. So there are just infinite number of possibilities. So how does algorithms take into account all these different possibilities and make predictions about whether that image is a cat or a dog? So these are the problems that modern AI tackles. The problems that are easy for human beings, that come naturally and intuitively for human beings, but where there are lots of possibilities, those are the problems that modern AI is targeting. Now, in order to solve these problems, people have tried out different approaches. One is the rule-based approach that we talked about, like playing chess, which turns out to be very accurate for easier problems, for some problems, but it is not sufficient to solve the problems like image recognition or object recognition or image classification or natural language processing or gene sequencing, etc. These are very hard problems for computers, even though they come naturally for human beings. So they tried rule-based systems, and there was another approach called knowledge-based approach. That is, you encode all the knowledge in the form of rules, and then computers try to make inferences out of those rules. That's a knowledge-based approach. But even that approach failed miserably. And at the end of the day, there was only one approach that was successful in solving these AI problems: a data centric approach, a data based approach, not the typical database in computing that we talk about, a data centric approach. That is, you feed data to a machine learning algorithm, to some mathematical model, and then the algorithm tries to understand patterns, tries to understand the data by recognizing patterns in the data. So you just dump the data at the model, and the model tries to understand the data by itself. The algorithm tries to churn the data and detect some patterns and build some knowledge about the data. The algorithm gains some insights about the data. Okay? And that's what machine learning is. So it's a subfield within AI. Machine learning is a subfield within AI. It's one approach to AI. Now, that being said, modern AI is all about machine learning. It can be contended that the data approach, the data centric approach, is the only viable approach to solve problems in AI. So if you are confused about AI and machine learning, just feel free to use them interchangeably. They mean the same in the modern era. All right. Now, within machine learning, there is a field called representation learning and deep learning. So when we talk about machine learning, we feed data to the algorithms, but we don't feed raw data, especially in traditional machine learning. If we feed raw data, the machine learning algorithms are not fully capable of understanding those patterns, of recognizing those patterns. So instead, we develop some features. We represent the data using some features. It's called feature engineering. And we feed those features to the algorithms, and then the algorithms are capable of understanding those, gaining insights into the data. Now, developing these features is a very intensive process, and it requires the domain experts, it requires a lot of time. It's actually more intensive and requires more expertise than machine learning itself. So there is one approach called representation learning, where you learn those representations automatically, and that's what representation learning is. Let's not go into it too much. But we want to talk about deep learning because these are the buzzwords: AI, machine learning, and deep learning. These are the terms that you would use if you're reading something about AI, or if you're listening to a talk about AI. These are the common phrases, common buzzwords that you would use, that you would listen to: AI, machine learning, deep learning. So I want to spend quite some time demystifying these terms so that you feel confident about them and you feel knowledgeable about them and you get motivated about AI. Now, what is deep learning? So, machine learning is a bunch of algorithms, right? It's a large set of algorithms like logistic regression, linear regression, support vector machines. We'll look into some of those briefly. So, it's a bunch of algorithms. Now, within those set of algorithms, there is one particular algorithm or method called neural networks, artificial neural networks. Most of you might have heard about it, ANNs. And they're just another function approximator. All these machine learning algorithms are function approximators. So neural networks is another function approximator. But it turns out that if you add a lot of layers into the neural network, if you make the neural network really big, then it can do very good. It can get very good accuracies on certain tasks like image processing or natural language processing, speech recognition, etc. So the study of neural networks with large number of layers has evolved into a separate field called deep learning. The neural network is pretty deep when you introduce lots of layers. So that's why it's called deep learning. Well, another reasoning that people give is it tries to understand the world in a hierarchy of concepts. So the smaller concepts are the concepts are arranged in a hierarchical manner, and the smaller concepts like eyes, lips, nose, etc., lead to understanding higher concepts such as face and person. So that's why it's called deep learning. When you arrange those concepts in the form of a hierarchy, then that graph is pretty deep, and that's why it's called deep learning. Right? So let's be clear about these three terms: AI, machine learning, and deep learning. AI and machine learning are almost the same. You can use them synonymously, and deep learning is a subfield within machine learning. All right, so let's stretch a little bit more about machine learning and what it is good for. What are the problems that we can solve with machine learning? Because if you want to use machine learning, it is pretty important that you identify the problems for which it is good. And even more important is, what is it not good for? What is it not suitable for? When you have a problem in front of you, you should be able to appropriately judge whether machine learning is suitable for the problem or not. So what is it good for? Let's take a simpler example, even simpler example, very simple example. It's called spam and ham problem, right? You have an email, you have a bunch of emails. Some of them are valid emails, and some of them are just spam. So the good emails are called ham, and the bad emails are called spam, right? So you want to be able to, given an email, you want to be able to automatically say, you want your algorithm to say whether that email is ham or spam. Or let's take another example. You want to take an image. So you have an image in your computer. An image is just a two-dimensional array of pixels, right? So you have pixel values from 0 to 255. If the pixel value is 255, the CRT shows a white pixel. And if it is 0, it shows a black pixel. And for everything else, it is some sort of gray color in between. And if it is a color image, you have three channels, red, green, and blue. So it's a 3D array. And each array is a two-dimensional array of pixels, right? Now, if you look at a raw image, all you have is numbers. So if you read a image into your, let's say, a C++ program or a Python program, all you get is an array of pixels, some random numbers that make no sense, right? Now, how do you say whether that random aggregation, random conglomeration of numbers is a cat or a dog without displaying it, right? How do you develop a program which can say, which can output whether that array of pixels is a cat or a dog? Now, if you start with your conventional programming style, you would just maybe write a bunch of rules. Let's say you take the average color, and if the color is white, or if it's close to white, then you would say it is a cat. And if it is close to maybe yellow or brown, you would say it is a dog. But then you will quickly see that it doesn't work for all the images. So you would add a few more roles, right? You may adjust those colors slightly, or you may change the shape. You may add a few more rules. But then if I give you 10 more images of different cats and different dogs, your program would again fail, and you would have to add more rules to your program. And you keep going on, and the number of rules just explode. It would be insensible to write such program and make it work for all possibilities. We need different algorithms. We need different approaches to solve such problems. We cannot brute force rules just like we do for maybe a sorting algorithm or a searching algorithm, right? So that's what machine learning is for. When you have complex set of rules that are impossible to code, or if the number of rules just explode, or you can, maybe you would develop a program for 10 images, but then if I give you 10 more images with different cats and different dogs from different maybe geographic locations, your program would fail. So you want your program to adapt to new data, and you don't want to write another set of long list of rules to adapt that to your new, to adapt your program to new data, right? So these are the kinds of problems that machine learning is good for. Okay, we talked about representations. Now, the The importance of using the right representations cannot be emphasized enough. And this is a pretty simple, straightforward example that shows why representations are really important. This is from Ian Goodfellow's book on deep learning. Um, the first few slides are introductory, like I said. So here we have a set of points on the left side. These are in Cartesian coordinates. And then the same set of points are represented in polar coordinates. Okay. Now, as you can see, if you want to draw a decision boundary between these points on the left side, you will need a nonlinear curve. You will need an equation of a circle or some other nonlinear curve. So you would not be able to use a simple logistic regression. Logistic regression is a linear draws a linear boundary between data points, right? So you would not be able to use a simple logistic regression for separating these data points and drawing a decision boundary. But if you represent these data points in polar coordinates, then you can simply draw a line. So any logistic regression or maybe a support vector machine with a linear kernel would just suffice to separate these data points and get very high accuracies. Okay. So representations are very important. Now, let's dumb this down a little bit and make it even clearer and simpler. Let's say you want an algorithm to predict, or an algorithm that can recommend whether a lady should go through a, let's say, a cesarean operation or a natural delivery. Okay. Now, your algorithm is going to take some inputs and then predict whether C-section is good for that lady or not. Right? Just binary classification problem. So you input information about this lady to the algorithm, and then the algorithm predicts whether the lady should go through C-section or not. If it is not, then it's a natural delivery. Right? Now, in this case, you need to give some sensible features to the algorithm, right? And the gynecologist or the doctor knows what kind of features are useful for prediction. Maybe the age, gender, of course. Gender is, of course, going to be female, but age, nationality, right? Weight, maybe body mass index, so on and so forth, right? You can come up with a bunch of features, and the doctor knows what features among those are useful for the prediction. So it is up to the user to give the right features to the algorithm. Right? You cannot just dump some raw data, useless data, and expect the algorithm to make a nice prediction. Okay, so that's one example of where representations are very critical. You need to give the right data, relevant features to the algorithm to be able to get some good accuracies. This is another slide that shows the difference between rule-based systems. All the programs that we write on computers, most of the times, if you are not using machine learning, then they are hand-designed programs, then they are mostly rule-based systems. Now, classic machine learning or traditional machine learning that has existed since decades, it requires these hand-designed features. For example, in the case of cesarean prediction example that we have talked about, the doctor or the user, whoever it is, needs to design the right set of features that will help the algorithm to make the right predictions. And in the case of representation learning and deep learning, we feed raw data to the algorithm, and there is an additional step where we automatically learn these features. That is, you dump all this raw data to the algorithm, like age, nationality, geographic location, maybe body mass index, weight, height, skin color, and a bunch of other features that we can think of. And in this case, in the case of deep learning and representation learning, we don't need a doctor. So we just feed all this raw data to the algorithm, and then the algorithm automatically learns what features are really useful for making the prediction. So that's the sort of new paradigm in machine learning these days, representation learning and deep learning. How do we learn these features automatically? Most of the time, over the last 2 decades or 3 decades, machine learning engineers have spent majority of their time in designing these right features. not actually using these algorithms, because at some point these algorithms doesn't make a whole lot of difference. So it's all about designing the right features. But nowadays, people are focusing more on deep learning, and here you don't need a domain expert, and that's why it is so appealing. Deep learning and representation learning is so appealing because you don't need a domain expert to design all those features, like doctor in the case of cesarean example, or if you're doing an image processing task like image classification, you need an image processing expert to design the right set of features, what kind of color histograms to use, what kind of shape features to use, or edges, or maybe texture, or perform some segmentation. So an image processing expert needs to design the right set of features for the algorithm. But in the case of deep learning and machine and representation learning, the algorithms are capable of deducing those features automatically. And that's why it is so appealing. Okay, so this is an enumeration of all the glorious machine learning algorithms. You might be familiar with most of these terms here. Uh, First, we have tree-based methods like decision trees, random forests, and gradient boosting. These algorithms tend to overfit. They might be suitable for certain algorithms, but they are very limited in capabilities. Then we have what are called GLMs, generalized linear models. Linear regression is a simplest example of machine learning, right? You have a set of data points and you try to fit a straight line to the data. That's machine learning. That's machine learning is all about optimization. Optimization is at the core of machine learning. So even the simple linear regression that you would do in an Excel sheet is a machine learning algorithm. Right? And then there are variants of linear regression like ridge, lasso, and elastic regression. They do regularization mostly. Logistic regression is a classification method. Support vector machines or another class of techniques. Then we have unsupervised learning. So let's talk briefly about supervised learning and unsupervised learning. These are two different approaches in machine learning. So in supervised learning, you have training data, and then the algorithm tries to learn from the training data. And then once you are done with the training, you deploy that algorithm in real world, and then the algorithm does the inferencing. So let's simplify this. Let's talk about a simple example. Let's say you have a 3-year-old kid who has not yet gone out, and he wants to know what a cat and a dog looks like. Or you want to teach your kid, so think of that kid as an algorithm, and you want to teach your kid the differences between cat and a dog. So instead of trying to explain them, what do? You take maybe 10,000 images of cats and 10,000 images of dogs. So that's 20,000 images. That's your training data set. And you, you gradually show those images to the kid one after the another, and you spell out loudly what it is. So this is a cat. And then you show the next image and say, this is a dog. And then you show the next image. Again, this is a cat and this is a dog. So you go through all those 20,000 images. That's one epoch. Now, the kid is dumb, right? The algorithm is just dumb. So you do that for 100 times. So you do it for 100 epochs. Each iteration is one epoch. So you go through this multiple number of times. The more number of times you go through, the kid becomes good at recognizing differences between cats and dogs. Now, once you train your algorithm, once you train your kid, you take another 10,000 images, 5,000 are cats and 5,000 are dogs. Then you show those images. This time, you don't spell out whether it is a cat or a dog. Instead, you ask the kid to recognize whether it is a cat or a dog. These 10,000 images are different from your training data set. This is your testing data set. And the kid now spells out whether it is a cat or a dog. So you train the kid, now you're testing the kid. And the kid maybe gets 80% accuracy or 90% accuracy or 95% accuracy. That's your accuracy of your machine learning algorithm. Okay, so there's a training data set and this is and there's a testing data set. Now, what I have described just now is supervised learning. There is another approach called unsupervised learning. In unsupervised learning, you don't have labels for your training data set. That is, you don't spell out whether it is a cat or a dog. Instead, you have 20,000 images. You just show it again and again to your kid, And then the kid says, there are two kinds of animals in this image, or maybe there are two kinds of creatures. He doesn't even know what an animal is. So he says, maybe there are two classes in these images, or maybe there are four classes. Okay, that's unsupervised learning. So the tree-based methods, the GLMs, all these are supervised learning methods. And then we have unsupervised learning techniques. Neural networks the uh, are the hot cake these days. Neural networks are like quicksort. Okay, if you most of you might have done some course in computer science, like basic data structures, like sorting and searching is what we learn initially in computer science, sorting algorithms. There are different kinds of sorting algorithms like bubble sort, heap sort, right? Radix sort, quick sort. Now, some of them take O of n square time and some of them take n log n time, right? Now, if I ask you which one is the most popular, maybe you're still in academia, maybe you're not familiar, but the most widely used sorting algorithm is quicksort, because quicksort turns out to be very good for practical usage. So if Google wants to sort 10 billion numbers, they would be using quicksort. Or if you look into your C++ STL standard template library, if you look at the sort implementation in the algorithms, the implementation is quicksort. So quicksort is the most widely used algorithm for sorting. Similarly, neural networks tend to be very good. And these days, for moderately complex machine learning tasks, most people are using neural networks. Okay. We'll go, if time permits, we'll briefly look into what neural networks are, why it is interesting, etc., depending on how much time we have. Now, I call them shallow neural networks because nowadays there is a distinction between shallow neural networks and deep neural networks. Neural networks have layers in between them. There is an input layer and there is an output layer, and there are layers in between them. So if you have more than one layer, it used to be very hard to train those algorithms. So initially, people used very shallow neural networks, like 2 layers in between. 4 layers is a lot initially. But nowadays, people are talking about neural networks with hundreds of layers. And there are reasons for that. Increased computation is one reason that's coming after. We'll talk about it briefly. Now, up to here is what I would call as traditional machine learning. Tree-based methods, GLMs, unsupervised learning techniques, shallow neural networks, and there are a bunch of other algorithms in traditional machine learning. Now, these convolutional neural networks, sequence models, autoencoders, etc., these are what constitute as deep learning. So a deep learning is not about just a deep neural network with lots of layers in between. People have come up with various topologies that are pretty good for certain tasks, like CNNs are very effective for image processing tasks. The RNNs or sequence models like LSTMs, and nowadays there are transformer models. These are very good for natural language processing tasks, time sensitive tasks like predicting the stock price, etc. Right. Autoencoders are good for feature engineering, and then generative adversarial networks are pretty classical and pretty new topology that has been invented by Ian Goodfellow. So this is what I would call as deep learning. Now, one more takeaway from this talk. Machine learning is all about data. Remember, in the first slide, we talked about different approaches to machine learning, and there is a data-centric approach that has become widely used, and AI is synonymous with that data-centric approach, and that is machine learning. So machine learning is all about data. We can do nothing without data. It's all about data. We can achieve nothing, we can do nothing without lots and lots of data, sufficient amount of data. It turns out that in real world, there are certain cases where we don't have enough data. And for such kinds of problems, we could use Bayesian inferencing. So if you remember Bayes' theorem from our high school, it's a conditional probability. It's a formula to calculate conditional probability. Now there is a whole branch of whole uh, field within statistics called Bayesian inferencing, and it's all about using our prior assumptions. So we have some prior assumption about a random process. So we encode that random process. We use that prior assumption as a starting point, and then modify it and then adjust it. That's what Bayesian inferencing is about. All right, and then there are these new learning paradigms called transfer learning, one-shot learning. If you don't have data, then there is something called one-shot learning. Like, for example, face recognition. You cannot expect to have lots of data, right? Face recognition is all about identifying the person just from one or two images that we have seen in the past, or from nothing, right? So one-shot learning is one such approach for face recognition. Semi-supervised learning and reinforcement learning, these are evolving fields. Well, reinforcement learning is a beast. It's been there for quite some time. All right, so if we look at a machine learning textbook or a machine learning research paper, this is what we would find, right? All these different glorious algorithms like neural networks, CNNs, RNNs, Bayesian inferencing, or hyperparameter tuning, and all these algorithms for hyperparameter tuning, these new paradigms like transfer learning, etc. But practical machine learning is all about processing data. Okay, data scientists or machine learning engineers spend only a fraction of their time in using these mathematical models. They spend 80% of their time in cleaning the data, understanding the data, getting the data into the right form, or integrating different systems so that you get the data to a point where you can feed it to your machine learning algorithm, etc. Okay. So if you have a bunch of data, don't just jump into machine learning. Try to understand the data first. And exploratory data analysis and descriptive analytics is the first step to understanding data. Just plot the mean, median, mode. Simple measures that we have learned in school. If it is multidimensional data, get pairwise plots or try to visualize the data, develop a relationship with the data, get some insights into the data before delving into the machine learning. Okay, that gives sufficient insight. If you have sufficient insight into the data, then you will be able to better judge what machine learning algorithm to use out of these seemingly numerous and endless machine learning algorithms. Data engineering, data augmentation. So if you don't have sufficient amount of data, then you can augment your data. For example, if you have an image of a tiger or a cat, then you can flip that data, flick that image, rotate that image, and do all sorts of image transformations on that image in Adobe Photoshop, or maybe you could use some programming tool to automate the process. But you could generate lots and lots of tiger images just from one single image of a tiger. And if you have 100 images, maybe you could generate 1,000 images. So you can augment your data set before feeding it to a machine learning algorithm. Bias detection and mitigation is interesting. So what is bias? We all are biased. Every one of us is biased in some sense, right? There is bias in the society. There is bias everywhere. There is racial bias, there is gender bias, there is age bias, right? Bias is everywhere. Now, bias may exist in your data because of these historical reasons, but going forward, you don't want your machine learning model to be biased. So if you feed data with bias to your machine learning algorithm, your model is going to be biased in making predictions, right? So let's say there is an emergency room and you are developing an algorithm to predict or to prioritize the patients. Right? Now, if there is a bias in your training data, then your model is also going to be biased. So you want to detect the bias and eliminate that bias and make your model fair. Interpretability is another important. It is becoming increasingly important, especially in regulated domains like healthcare and finance. For example, if you're a finance institution and you reject a loan for your customer, especially in US, you're supposed to give an explanation for why you have rejected a loan, right? And you cannot simply say, my model has suggested me to reject the loan for this person, and it suggests that there is a high risk of this person not repaying the loan. That's not enough, right? You're supposed to give a valid reason. So if your algorithm, if you can get some insights into your predictions, why your algorithm is making the prediction that it is making, then you would be able to give those explanations and satisfy the regulatory committees. Right? That's what interpretability is. Now, people use all kinds of different terms like explainability, fairness, accountability. I just club it all of them into one term called interpretability. Because if you can understand your model, if you can understand why your model is making the predictions that it is making, then that is sufficient to get to achieve fairness and accountability and transparency and ethics. All of that follows. So it is important to understand why the model is making the predictions that it is making. Now, why is this even an issue? Why are we talking about interpretability? If you're not familiar, the neural networks in all their glory are, are notorious. They're called notoriously called as black boxes. That is, neural networks are very good. Let's say you developed a model for predicting animals like cats, dogs, lions, tigers, and a bunch of other animals, and you feed the data to your algorithm, maybe a million images. Then nowadays the algorithm can be 99.99% accurate in predicting those images, predicting those animals, but you won't be able to explain, or you won't be able to look into it and say why it is able to predict, why it is able to achieve such high accuracy. It's more statistical tool, right? So they're called black boxes, and that is not sufficient. That might be good for scientific use cases, but that is not sufficient for the regulated domains like healthcare and finance, like we talked about, right? If your model is making predictions, or if your model is prioritizing the people standing in a queue in an emergency, at an emergency line, in a queue for emergency ward, then you cannot just blindly follow your model to prioritize the people, right? Either your model should be able to predict, your model should be able to explain why it is prioritizing one person over the other. Okay. Then there is inference optimization. We'll talk about inference briefly. Let's see if that is the next slide. Let's talk about this briefly. So AI is making a difference. It's making an impact across the scientific fields and also in the industry, not only in academia, but also in industry. So these are all the different areas in which AI is making an impact, like financial services, there's retail, there's law enforcement and defense. AI is being adopted everywhere. And whoever jumps onto this train first, if you are in research, then whoever jumps onto this train first, if you adopt AI for your research, you will be able to make some significant contributions and maybe publish some good papers. Whether you are a geologist or a mechanical engineer or chemical engineer or civil engineer, it can be adopted across the fields because there is lots of data that has been collected over the decades with all those sensors, and there is lots of data that needs to be understood, and it is AI and automation is the only viable approach to gaining insights into the data, right? We all are experiencing the data explosion in the form of transactions, the YouTube videos, or whatever. It is human impossible to comprehend the data that is exploding, right? And AI and automation is the only approach to gaining some insights and getting a handle over this data. Right, we talked about supervised learning. So in supervised learning, there is a training phase and there is an inference phase. Okay, we talked about training a kid by showing those 20,000 images again and again, right? That is all training. And then we also do the testing, right? And then we deploy the kid into the real world. That is, we ask the kid to go outside and identify cats and dogs. That is inferencing, okay? So training and testing is part of the training phase. Now, training is compute intensive and inference is relatively cheaper. If you think of the example that we talked about, You want to show these images, 20,000 images again and again to the kid. You want to do it for 100 epochs or 1,000 epochs. That's going to take a lot of time compared to asking the kid to just identify cats and dogs when he is doing in the real world. Okay. So training is typically done on heavy compute infrastructure like high performance computing clusters or maybe cloud resources. And inferencing is relatively cheap, right? It could be in a Apple Watch, or it could be in an iPhone, or it could be in a maybe 1,000 feet underwater system where there is no internet. Okay. Once you develop your model, once you train your model, once you have a working model, you don't need anything to infer from that model. All you need to do is you need a small computing device, and if you can feed your model into it and you feed the input, then you would be able to make the inference. So you don't need internet. So you might be able to, you may want to do that inferencing in a maybe seabed, who knows, right? So inferencing is cheaper, and inferencing could be deployed in various locations. There are in any location, whereas training is typically done in a high performance computing infrastructure. So what can you do with machine learning? What are different kinds of tasks? Regression is one task, the linear regression. Let's say you have a stock price from the last 3 years and you want to predict where the stock price is going tomorrow. That's a very basic model, and nobody would use machine learning to predict the stock price. That would be a very unprofitable approach. But anyways, regression, that is one example for regression. Classification is the example that we have been talking about, cats and dogs. So you could use the machine learning algorithms that we have discussed here, right? The tree-based methods, the GLMs, the neural networks, etc., to perform these tasks like regression or classification or anomaly detection. These names are straightforward, right? Anomaly detection is identifying a needle in a haystack. Density estimation is understanding the probability distribution of the data. All these machine learning algorithms either implicitly or explicitly estimate the probability distribution of the data, of the training data that we are providing. Okay. In the case of density estimation, we estimate the probability distribution explicitly. And clustering is one example of density estimation. It's a quintessential example of density estimation. In structured output, uh, the output is a vector. So a simple example is language translation. Let's say you want to translate a sentence from English to French, then the output is not just a bunch of words, but those words are related to each other. So it's a structured output. In synthesis, maybe you can generate music from your machine learning algorithm. It would be intolerable, but you can still do that. Or you can synthesize a piece of text. You might have seen these examples, synthesizing Shakespearean text, Shakespearean paragraphs from nowhere. I mean, they're not readable, but they sort of look like Shakespearean text. Synthesis is still evolving, but we will be making good progresses in synthesis as well. Denoising is self-explanatory. So these are the different kinds of machine learning tasks that can be performed using the machine learning algorithms. This is not an exhaustive list. It is just an enumeration of the common machine learning tasks. Okay, you could do a lot more. All right. Now, you might have heard about AI and machine learning a long time ago, right? And everybody has heard about it. AI existed since almost decades. In fact, when people invented computers in 1945, people started thinking about how intelligent these machines can be. Right? So AI is not new. Machine learning is not new. It existed for decades, maybe 70s and 80s, since the 70s and 80s. And deep learning is also not new. The convolutional neural networks, the first paper on convolutional neural networks was published in the late 90s, 98. Right? And RNNs are not new. So all these deep learning topologies are not new. Nothing is really new. Nothing is completely new. So why are we talking about AI now? What is changing? What has made machine learning more appealing for people beyond the computer science department? These are some of the reasons. First thing is data explosion. Like we talked about, machine learning is all about data, right? The more data we have, the better it is, and the more accurate the algorithms will be. So if you're developing a algorithm, and if you don't have sufficient data and you get 60% accuracy, that's that's not useful. That's not very useful for real world applications, right? And 50%, let's say you're doing a binary classification, then just a random selection would be 50% accurate, right? So you have to be at least 50% good. The machine learning algorithm has to be at least 50% good. So accuracy is important for real world applications. And previously, there wasn't that much of data, but now we have lots and lots of data. We all are experiencing this data explosion. So there is enough food for the machine learning algorithms to be able to perform better. Okay. And that's why machine learning has become very interesting these days. The second reason is GPUs. GPU stands for graphical processing units. Okay. GPUs and SIMD architectures. SIMD starts for single instruction, multiple data. Now, what are GPUs? Well, GPUs are graphical processors, right? Almost all of our computers have some sort of graphics processor to be able to process this graphics pipeline and display the images on our computers. But those are conventional graphics processors. And back in 2007, NVIDIA, you might have heard about that company, NVIDIA has developed a programming interface called CUDA that allows GPU programming. So GPUs are very good for scientific computations. The architecture of the GPUs, it's a SIMD architecture, single instruction, multiple data, and that architecture is very good for scientific computations like numerical algorithms and AI workloads. So these neural network computations, the support vector computations, the generalized linear models, all of these boil down to massive linear algebraic operations. So no matter they might be taking hours of execution time, but when the computation goes and hits the bare metal, it's all elementary algebra at blazing speed, at scale. Like you may want to do a million by million matrix multiplication, but it's just matrix multiplication. Yeah? And GPUs are very good for executing them very quickly. Think of it this way. This is electrical department, right? So if you make the transistors faster, the computation is faster in general, right? So at the hardware level, the computers are a bunch of transistors, right? So if you can make the transistor faster, then the computers, the applications are faster in general. And you may have to worry about maybe clock jitter, etc. But the primary goal of the engineer initially, at least, was to increase the clock speed of the transistor, right? Because if you can speed up the underlying hardware, if you can make the underlying hardware faster, then the entire applications, the application stack sitting on top of those transistors is going to be faster. Similarly, in the case of machine learning and deep learning, the algorithms boil down to massive linear algebraic operations, vector operations, maybe matrix vector multiplications, right? Or matrix multiplications, etc. So it's all elementary linear algebra when the computation goes and hits the bare metal. If you can make those computations faster, if you can make those linear algebraic operations faster, the machine learning algorithms, the entire machine learning workloads are going to be faster in general. And GPUs, the graphical processor units, the graphical cards that we have in our computers to display the graphics, turn out to be very good for speeding up these algebraic operations. Okay? And NVIDIA has developed a programming interface to use these GPUs for scientific computations. That's what CUDA is. Okay? CUDA and CUDA-C. and that has changed things a lot. So anybody can implement these machine learning algorithms on GPUs and make them faster. Okay, some of these machine learning algorithms take pretty long to train. Microsoft has trained ResNet for 16 days. Okay, that's longer than any vacation that I have taken. Okay? So these machine learning algorithms take very long to train, and GPUs can bring down the time to days or hours. So if you're not using GPUs and if you're doing deep learning, then you're wasting your time. Okay, so you have to use GPUs to be able to make progress with deep learning applications. And then there are some advancements in neural networks. We talked about neural networks. There have been some advancements like addressing vanishing gradients. Everything comes at a price. So if you increase the number of layers in your deep neural network, then you run into this problem of exploding gradients and vanishing gradients. That was a problem. It was not thought of before, but with people starting using these neural networks with deep layers, there have been techniques deduced for addressing this vanishing gradients problem. That's leaky ReLU. ReLU stands for rectified linear unit. You can just search them. I'm just going to introduce a bunch of terms here. I know I'm introducing a lot of jargon, but like I said, my goal is not to teach machine learning in this 2 hours period, but to motivate you to learn about machine learning by yourself and use it in your teaching projects and research projects. All right, Radhika, I need some feedback here. Do you want me to continue, or do you
Sir.
want to wind up?
Hello, sir.
Yes,
Uh,
I need some feedback here.
yes,
Do we
sir.
want to continue? Do we want to simplify or go into more? I can do anything. I can go on.
Sir, your convenience, sir, as it is very late night to you, I can understand. Your
Okay.
convenience, sir.
Okay. All right. I'll take maybe another half an hour and then we'll stop it.
Okay, sir.
Sure. Okay.
Thank you.
All right. So artificial neural networks. Now, the term neural networks is a little bit misleading. It has nothing to do with brains. Well, it has something to do with brain, and let me demystify that. Let me throw some light onto why it is called neural networks. Okay. So this image here is the image of a neuron. Okay. And we have these purple lines called dendrites, and there is a nucleus. These dendrites receive signals, and then the nucleus processes it and then sends a pulse along this axon, which is connected to the other dendrites. Okay? This is how a neuron looks like. And then if we open up our skull and look inside, it's a bunch of these neurons that are connected together. And human brain has billions of such neurons. Right? Now, a logistic regression, this is how a neural network looks like. A neural network looks like. This circle here is a mimicking of this neuron here. So it takes these inputs and then it processes them and it sends a pulse to the other neurons that are connected in the next layer. Okay, so the neural network is a mimic of the structure of the human brain. But like I said, this is a vulgarization of the human brain. Okay, this is not even close to how a human brain is structured. But it turns out that this is a very good function approximator. All these machine learning algorithms, think of them as function approximators. That is, when you look at a cat or a dog, you're looking at an image, you're looking at a bunch of pixels, and there is some function that is you're feeding that input x to your brain, which is f. The f of x is the output. You say whether it is a cat or a dog. So it's a function, right? We assume that there is some function going on in our brain. And we are trying to approximate what that function is with machine learning. So machine learning is all these algorithms are function approximators. So this neural network turns out to be a very good function approximator. In the input layer, you just feed those features like age, maybe height, weight. And then the output, in this case, we have 4 neurons in the output layer. But if we have only one single output, then it could be predicting what is the recommendation, either it says recommend or not recommend, right, for a C-section. So these are function approximators. Now these are the hidden layers. So if it is a function approximator, you don't need this diagram, right? You could just write all that entire function in the form of a equation, but that would look huge and ugly. And that's why we use such sort of representation, which makes it very clear. And it is easy to communicate with others if we are representing the function by means of this diagram. Okay, this is how a neural network looks like. There is an input layer, there is an output layer, and there are hidden layers in between. In this picture, there are two layers, but in the case of a deep neural network, you could have 100 such layers. What we have shown here is called a fully connected neural network. Okay, and there are other topologies like CNNs, RNNs, etc. They differ in how these neurons are connected to each other. Hmm. Now, it's all about optimization. So we define an optimization problem. In order to do that, we need an objective function. So this is the cost function. This is our objective function, and we want to minimize it or maximize it. Let's say we want to minimize it. So our goal is to find the global minimum. This is what is called a non-convex function. In the case of a convex function, you have one global minimum and you don't have any local minimums, right? But in the case of a non-convex function, you have multiple local minima. So it is very likely that you would end up in one of these local minima. Our goal is to pass those local minimums and try to minimize the cost as much as possible so that we can get high accuracies on the machine learning, so that we can get high machine learning accuracies. All right. Why I know I understand this is getting a bit intensive, but my goal here is to help you, give you some intuition into why we need GPUs for neural networks. Okay, for training neural networks. So training this neural network here boils down to two steps called forward propagation and back propagation. And if you enumerate the formulas for this forward propagation and back propagation, it all boils down to massive linear algebraic operations. It's all about matrix multiplications and matrix vector operations. It's all SIMD parallel operations. Okay, and that's why we use GPUs so that we can make them faster. All right, so what are some applications of deep learning? Computer vision is the image processing has just exploded because of deep learning. Okay. Back in 2004, 2003, some of the machine learning algorithms, some of the image processing algorithms were really hard, like image classification or object identification, etc. But now, because of the advancements in deep learning, the computer vision field has made huge progresses in these basic image processing tasks. Natural language processing, that is name entity recognition or understanding a piece of text, language translation, etc. There are some good progresses that have been made. Speech recognition has made huge progress because of deep learning. If you have never tried it, I would suggest try recording a video and uploading it to YouTube, and then see if you can identify turn on the language translation, and the subtitles are pretty accurate these days. And I tried it back in 2005. We had to train the speech recognition algorithm for quite some time and personalize it for our speech recognition. But even so, the IBM Via Voice was the state of the art back in 2005, and it was not accurate enough. But now you just randomly record a video or an audio and upload it to YouTube and see how the translation works. It's pretty accurate. There are some use cases in bioinformatics and chemistry, and then quantitative finance as well, like options trading, etc. Okay, so this diagram is from Andrew Ng. On the x-axis, we have data here, and then y-axis is performance of the machine learning algorithms. So this red line here is the traditional machine learning algorithms. So why do we need deep neural networks? Because we have lots of data these days, and we can get very good performance with feeding more and more data. Okay. When we say more data, we are talking about millions of images, feeding millions of images to these machine learning algorithms. Okay. I think I'll just skip this. And these are some applications of computer vision, like object recognition, object detection, segmentation, face recognition. You might be hearing about these a lot when you're listening to machine learning and deep learning talks. Now, deep learning in all its glory, it's all about using neural networks with lots of hidden layers, and they're notoriously called as black box models because you won't be able to accurately or effectively explain why the models are making the decisions that they are making. So that is why the traditional machine learning algorithms like decision trees or even linear regression or logistic regression, the gradient boosting is very accurate, support vector machines. All these traditional machine learning algorithms are equally important. In fact, despite these high accuracies with deep learning algorithms, if you have some data in front of you, I would suggest start with the simplest model and then gradually build upon it. Because, like we said, these are function approximators. The function between an input and the output has to be complicated enough, it has to be complex enough for you to deploy deep learning algorithms. So, if it is a simple binary classification, maybe a logistic regression or even a naive Bayes classifier would be sufficient to accurately make the prediction. And if you use more complex model than you need, you would end up overfitting. Overfitting is another jargon that you may want to familiarize yourself with. What is overfitting? We talked about the example of showing the images to the kid, right? So if you show that image, if you show the same 20,000 images to the kid again and again for maybe 10,000 times, the kid gets so specialized in recognizing just those 20,000 images that he performs very poorly on the testing data set. So if you show those new images, the kid won't be able to generalize his knowledge to those new images. Okay, that's overfitting. So you run into this problem of overfitting when you're doing machine learning. And neural networks, if your function is not complicated enough, if it is not complex enough, and if you use a complex model instead of using a simple model, then you would most likely overfit to your training data set. Okay, that's why if you have some data, start off with simpler models. And interpretability is again another reason why you may want to be interested in traditional machine learning algorithms. These are some retail use cases, pricing optimization, promotion optimization. These have been existing since a couple of decades. But what has changed? Data. There is more data, so you can make all these use cases, you can make all these models more accurate. Same with financial services use cases like credit risk assessment or asset valuation. All these use cases have existed. There are machine learning models out there, but now that you have more data and you have improvised technologies, you can make them more accurate and introduce more automation into your workflows. All right, this could be interesting. So, what is the goal of this slide? The goal here is to convince you that you don't have to be a computer science researcher to be able to use machine learning. Every one of us can use machine learning, and these are the technologies that are democratizing machine learning. First, machine learning is compute intensive, so you need high performance computing architectures. But these days, anybody can assemble a small system with a GPU, and that's good enough to develop moderately complex machine learning algorithms. Okay, you don't need supercomputers to be able to do machine learning these days. And then there are these open source deep learning frameworks like PyTorch, TensorFlow, and Keras. They provide very good high level abstractions to machine learning and hides the complexity of these machine learning algorithms. Like we talked about forward propagation and back propagation in deep learning in neural networks, you don't have to implement all of that. You don't have to code it up. They're all abstracted away, and you just can program at a very high level of abstraction. In fact, there are some graphical user interface based tools where you don't need to know any programming to be able to do image recognition, okay, image classification. All right. And then data processing libraries like Pandas, QDF, Dask, Dask QDF. If there are any students in the room, I mean, most of the most common question that I get is, what programming language should I be learning? And I say, learn the algorithms. Programming languages, programming tools are temporary. Algorithms are eternal. So focus on the algorithms, and there will be plenty of time to specialize in any programming language. In fact, nowadays, nobody specializes in one programming language. You should be able to use whatever that is needed and whatever is most appropriate for the task. So if you focus on your algorithms and your methods and the underlying math, then you will be able to easily uh, leverage any programming language. Okay. I'll skip this slide. I'll skip this as well. This is all about IBM. I can talk a couple. I think I'm representing IBM, so I think I need to call. It's my dharma to talk about IBM. Okay, so we have what is called a Watson machine learning accelerator. It's a tool. It's a product that we sell. It's a hardware software co-optimized solution. So we talked about these frameworks like TensorFlow and PyTorch. We get all of them as one single binary, and then there are easy to use tools on top of it. So you get the hardware, you get all these frameworks, and then there are some easy to use tools on top of it, so that you can do machine learning pretty easily. And then these are the additional features. So we not only focus on deep learning, but we also have something called SnapML. It allows you to do machine learning at scale, that is terascale. So you can feed your logistic regression with terabytes of data and get pretty good accuracies. Then if your distributed training is about distributing the computation to multiple GPUs and multiple servers. So you're not only using one computer for your training, but you're using a group of computers for training your machine learning model. Okay, that is distributed machine learning. And you don't have to implement all of that from scratch. Instead, you can use this high-level API to be able to easily do distributed training. We talked about data preparation. So machine learning is all about prepping data, understanding data, and converting data into the right forms. Okay. Only 10% to 20% of the time is actually expensed in building this in the real mathematical models. Most of the time is spent with data. Then we have something called large model support. AutoML is something that I would suggest you to look into. There are some computer vision based automatic machine learning tools for computer vision tasks. Like AI Vision is an IBM tool, and I'm sure there are a bunch of others. I can't recall the names, but you don't have to do any programming. You don't have to do you don't have to know computer vision, or you don't have to know image processing. So it's a GUI based tool. You just feed a bunch of cats and dogs, or maybe a bunch of animals images to the algorithm, to the tool, and then you can build your classifier. You just hit that one button, it builds a classifier, and then when you upload a new image, it would be able to say whether it is a cat or an animal or a dog or a horse, etc. Okay, so that would give you some preliminary insight into what machine learning is and what it is doing. All right. Okay, I have this slide, and maybe I'll talk about ocean engineering. That could be interesting, and then we'll wind it up. So I think we should all fail fast in AI. What does it mean to fail fast? You quickly fail so that you can recover and do something different. Okay, and these are the reasons why you should fail fast in AI. You should fail fast and you should fail better. Okay, so you don't want to spend 6 months or 1 year going down one path and then realize that you are on the wrong path, and then wind back and then start again. Instead, you should be able to do it in the span of weeks. You should be quickly realizing that you are not in the right direction, and then switch gears and switch direction, especially in AI. And the reason is AI is an experimental science. So you have looked at all those bunch of algorithms. There is something called no free lunch theorem. What it states is, if you don't make any assumptions about your data, if you don't know anything about your data, then there is no advantage to choosing one algorithm over the other. Okay. So if you know that, if you know something about your data, if you understand your data, then maybe you can choose the right algorithm. But if your data is new and you don't have any insights into the data, and if you're not making any assumptions on the data, then every algorithm is the same. So you just need to try out all those algorithms to find out which one is good for you. Okay. The software ecosystem around AI is rapidly evolving. That is, we talked about these frameworks like TensorFlow, PyTorch. They are quickly evolving. There are nightly builds, and 3 months is a long time in AI. They come up with new features. So you don't want to specialize in one framework. Instead, you want to be able to quickly hustle with these different frameworks. The software engineering practices are not yet established. What does that mean? In the case of traditional software engineering, there are testing methodologies, there are design patterns, there's a software development lifecycle. So there is some conventional wisdom that has been recorded, right, in the case of traditional software engineering. But in the case of AI, such practices are not yet established, they're still being developed. The software engineering aspect of AI is still in its infancy. Even though AI has advanced, the software aspect part of it is still in infancy. So you don't want to spend a lot of time, you don't want to devise those practices by yourself by working on it for 1 year or 2 years unless that is your area of interest. If your goal is to solve some machine learning problems, you want to quickly try out something and quickly fail and turn direction or change direction. And then parallelization is a way of development. So parallel computing, in the case of, if you're writing a numerical simulation, say if you're writing some traditional program, you would first write it, get it right, and then parallelize it. But in the case of AI, you should embrace parallelism from day one. So if you're using deep learning, or if you don't have a GPU, but still, I would encourage you to just use multi-core processors, multi-core systems, even if you don't have a GPU. Don't do AI on your laptop. Use a server if you have it in your reach, so that your training time is reduced and you can quickly iterate and make progress. Right. So this is a use case in ocean engineering. Uh, Dalhousie University in Nova Scotia, Canada, was interested in this use case. They were trying to use machine learning to detect the reason for the death of whales. Okay. So Atlantic right whale is an endangered species. There are fewer than 500 Atlantic right whales that are alive right now, and the marine biologists can recognize them like family members. There are only few of them, and they're continuously watching them. It's an endangered species. And despite all these efforts, 17 whales died last summer in Atlantic Ocean. Here we can see the picture of a whale that has died on January 22nd, 2018. Okay. So the goal here is to understand why these whales are dying. The primary reason seems to be the ships striking against these whales. So, but the researchers are not sure. There is a lot of pressure on the researchers to understand why the whales are dying. Okay. So they're using machine learning for this task. And the way it works is they install a lot of acoustic sensors in ocean waters. Let's see if we can play this video. No. Okay. Anyways, you can just search for a whale sound on YouTube and you would be able to listen to a whale sound. You would get a feel for what we're trying to do here. So, a lot of acoustic sensors are installed in the ocean waters, and then we record the sounds that are being made in the ocean. In an ocean, there is a lot of ambient noise. Like the whales are making sound, the whales are making sounds, but at the same time, there is a lot of ambient noise, like maybe the noise of the wind, the noise of the waves, the ship sirens, etc. There is a lot of noise from other animals, the sound from other animals, etc. So it is hard to recognize a whale sound. And the marine biologists manually listen to those audio signals and then classify it as a whale sound or not a whale sound. Now, the goal of the researcher here is to understand to use machine learning to predict whether a given audio signal is a whale sound or not a whale sound. And this is a workflow that they have used for that. So you have raw acoustic files, that is, this is the audio signal. You do segmentation and convert it into a frequency domain, and then you use some sort of ocean sound classification algorithm. So this is the machine learning module. It would recognize whether that sound is a whale or not a whale. And then we have something called AIS database. AIS database is the uh, data from the ships, from all the ships across the oceans, where the ship what are the ship locations, what speed is it going at, what is it? Is it a cargo ship or is it a passenger ship, etc. So there is lots of data. The AIS transponders are embedded into the ship infrastructure, and it sends data to the satellites. Right? There is a lot of the ships are being tracked in real time. So we know where the whales are, and we know whether they are whale sounds or not, and we know where the ships are. So we could use that information to develop some algorithms that detect ship collisions, okay, and then build some whale conservation strategies on top of it. So this is a very broad research program, but hopefully it gives a sense of where machine learning is being used in these cross-disciplinary fields, such as ocean engineering. Okay, I think I'll stop here. Uh, Happy to take any questions.
Dear participants, now the session is open for the question and answers. If you have any queries, please post in the chat box or you can directly unmute yourself and can ask.
Okay, no questions. Hope that was not too intensive. Let's see the chat window, see if there are any questions. Oh, there are quite a few questions, Radhika. I'm sorry, I haven't looked at the chat window. Okay. Machine learning is a subset of artificial intelligence. Okay, making computers to take decisions by themselves. That's right. Kindly share this video PowerPoint. Okay, I will send the PowerPoints to Radhika and you can share them.
Sure, sir.
Please suggest the PC configuration for deep learning algorithms for research. Any Intel system would do. I mean, the PC configuration is not so critical. Any Intel server, but if you are wanting to do deep learning, that is, if you are wanting to train neural networks or convolutional neural networks, recurrent neural networks, or autoencoders, you want to use GPUs because GPUs would make your life a lot simpler. A single GPU is also good enough. It costs, and here it costs about $20,000 to $30,000. But if you're serious about deep learning, then GPUs will make life a lot easier. That being said, I think I have made it clear during the talk. First, make sure you need deep learning for most of the tasks. In fact, even in my case, when I go to customers and when I go to universities, what I am finding is most of these machine learning problems that our customers have can be solved with simple machine learning algorithms like naive Bayes, logistic regression, gradient boosting, etc. Gradient boosting is faster on GPUs, but you could pretty well train your algorithms with CPUs as well. Now, GPUs are accessory devices, right? GPUs don't exist in isolation. GPU is always coupled to a CPU. So if you have a CPU-based machine, any Intel server, or IBM has something called Power machines, Power 9 and Power 10. They tend to be a little bit expensive. They're Power 10, we call it AC 922, it's about 100K. But these are rough figures. But if you are using traditional machine learning, any system would do. I mean, you want to find the hardware, and then on top of that, you want to use the frameworks like TensorFlow or PyTorch. You don't want to code it in C++ or Python. You don't want to do that low-level programming. That's not your goal. Your goal is to do research, right? So use one of these open source machine learning frameworks for your to quickly do some development. And there is something called Jupyter Notebooks that you might already be familiar with, the Python notebooks. It's a web interface to the programming. Okay? They are also very helpful. We have seen command line, we have seen punch cards, and then we have seen these Visual Studio and Eclipse with the graphical user interfaces, the graphical programming tools. And now this is the era of web-based programming tools. So I call these Python notebooks as fourth generation programming tools. Okay. So Jupyter notebooks can be used for execution, for compilation, for visualization. Everything can be done in the browser itself. So you definitely want to use Jupyter notebooks and Python frameworks, Pythonic frameworks, and a Pythonic environment. The hardware is not so critical. I mean, if you're doing machine learning, then just, I mean, we can do one-on-one and we can go into detail on, well, my goal is to sell IBM servers, so I would be happy to sell. But in most cases, you may be better off with doing traditional machine learning. All right. Feedback link. Okay. Deep learning, machine learning, AI is good for STEM, science, technology, engineering, mathematics, management, and medical also. Research areas. You could think of pretty much any research area, I mean, like oil and gas, seismic wave inversion, right? Or reservoir simulation, or quantitative finance, like options hedging strategies. There are applications everywhere, right? So the traditional mathematical models are, they do a pretty good job, but they are not, but by using machine learning and deep learning, you can deduce models from the data. So it's like evidence-based approach. You have the data there and you're building your model based on your data. In the case of traditional science, you develop your formulas, you develop your hypothesis, and then you develop your formulas based on your understanding of the world, right? But in the case of machine learning, you collect data and you use the data. It's sort of reverse engineering, right? You get insights, you build your models, and you build your formulas from the data itself. So you could think of applications in a broad variety of areas, like ocean engineering that we have seen. I have another example where they have used deep learning in museum science. Okay? There are some Egyptian scriptures that were very difficult to understand, and they use CNN, combination of CNNs and RNNs to make sense out of those scriptures. So there are applications everywhere. May I know the prerequisites for deep learning? I need a little bit more information here. What do you mean by prerequisites? To do deep, I assume it is, what do I need to know? What do I need to learn to do deep learning? Well, programming is one part of it, but if you're using Python, then it becomes a lot easier than using C or C++ or Java. And then apart from programming, you want to have some understanding of what those algorithms are. So there are plenty of online courses these days. I mean, the education is just free everywhere. The Coursera has plenty of courses. Andrew and then NG Eng is a very famous guy. He has lots of courses for novice machine learning engineers and for non-computer science experts. Okay, machine learning for everybody. So there are plenty of courses there, and it helps to develop some initial insight into what a machine learning algorithm does. And then you don't have to know the glorious details, because deep learning is a field in itself, and there is lots of jargon, there is lots of, and it's changing so fast. But if you develop some initial insights into what a machine learning algorithm does, start off with basic linear regression. You can understand, you can explain the entire linear regression with a, you can explain the entire machine learning process with a linear regression. You can talk about training data, you can talk about models, you can talk about parameters in the model, you can talk about testing data, you can talk about inferencing. So by starting off with a basic linear regression, you can get a pretty good understanding for the entire flow of a machine learning process. We can talk about outliers, right? We can talk about data cleaning, we can talk about exploratory data analysis, descriptive statistics, we can talk about pre-processing. Just using a simple linear regression, you can understand the all aspects of machine learning process. Okay. And then from linear regression, jump on to logistic regression, which is the first classification algorithm. It's called regression, but it's still a classification algorithm. Okay, and logistic regression gives enough background to understand neural networks. We have gone through it briefly. We looked at a neural network um, diagram, and we looked at some cost function. If time permits, I would be happy to go through a detailed tutorial. But if you get some initial insights into how a logistic regression works, then you can develop insight into what a neural network is. And you don't have to know the glory details of what a CNN topology is, what a RNN topology is. But once you have this basic knowledge, you would be able to use those. And then the frameworks like TensorFlow and PyTorch. I think it is too early to specialize in any one framework. So I would just pick one, maybe TensorFlow, and just stay with it because these frameworks are rapidly evolving. They make life easier a lot, but at the same time, they're rapidly evolving. So it is too early to specialize in any one framework over the other. How can we apply deep learning in wireless communications spectrum? That's an interesting question. Wireless communications, I am not sure. I think I'll pass this question. But there is a lot of investment in AI by the telecom companies like Verizon and AT&T. Let me see if I can recollect a use case from Verizon. Yeah, I would have to look into it. I don't recall, but there was some use case by Verizon where they were trying to predict the. Yeah, I would rather not answer instead of giving a wrong answer. Any free and open source softwares for AI ML suggested for learning purposes? There are tons. So I would let me go back to this slide here. So these are the frameworks here: open source deep learning frameworks and traditional machine learning frameworks, automatic machine learning frameworks. These three bullets, I would say start off with scikit-learn. Scikit-learn is a traditional machine learning algorithm framework. So you could do linear regression or logistic regression. H2O is same as scikit-learn from a feature standpoint. Okay, so just skip H2O and maybe use scikit-learn. XGBoost is for gradient boosting. Gradient boosting is one kind of algorithm. So start off with scikit-learn and XGBoost. They're pretty easy to pick up. And once you are done with this traditional machine learning, then you can jump on to PyTorch and TensorFlow, which are more suitable for deep learning algorithms. Well, you could still do a linear regression in TensorFlow, but I don't see any reason why to do it if you could do it in scikit-learn or H2O. Now, if you're even a novice and if you don't want to do programming, try H2O driverless AI. This is a very easy to use, very intuitive tool, and it gives some pretty good insight. It shows the features that are being used, what is the importance of the features, etc. So going forward, there are going to be a lot of these tools which make machine learning even more easier. And the automatic machine learning frameworks are still in infancy, but they are going to be better and better as well. So these AI vision, H2O driverless AI, and data robot are graphical user interface based tools. They are GUI based tools, so anybody can use them. The auto sklearn teapot uh, are more for the nerds, so they are mainly used for hyperparameter tuning, etc. So I would skip these. Instead, start off with these H2O driverless AI. I think you could get a free trial. I think for data robot also you can get a free trial. See if you can get a free trial and just play with them. Then once you are done with this, see if you can play with scikit-learn and write some small Python programs and do some basic tasks. If you're done with this, then move on to deep learning and see if you can play with PyTorch or TensorFlow. Okay, Keras is a higher level abstraction to TensorFlow. Computer science is all about building these abstractions, right? People used to write in binary, people used to write programs in zeros and ones, right? And then there was assembly language, and then there's higher level languages, and then we have APIs on top of it, right? So TensorFlow is a high level abstraction, but even on top of it, there is something called Keras, which makes it even easier. So the more higher abstractions we have, we lose the control. So with TensorFlow, you get a lot of control. With Keras, you lose some control. But nowadays, TensorFlow and Keras are just being used. Uh, People are writing Keras calls in TensorFlow, and TensorFlow also provides a module for Keras. So it's just a part of TensorFlow. And what Keras is to TensorFlow, Fast AI is to PyTorch. Okay. Please share, if possible, those case study. It will be helpful. Okay, yeah, I will just pass on the information to Radhika, and she can share it with everybody.
Sure, sir.
Attendance link.
That's when I posted.
Okay, all right. Okay, thank you. Thanks for your comments.
Thank you, sir. Thank you so much for your valuable insights. It is really a valuable session on artificial intelligence. I know, sir, it's very late night to you, but you really supported us. Thank you so much.
Not a problem. My pleasure.
Thank you, sir. And dear participants, the afternoon session starts at 2:30 p.m., followed by the valedictory. At the end of the valedictory, we have the assessment, and that link will be posted at that time. So based upon your score, the participation certificate will be given. Thank you all. Let's wind up the session and meet in the afternoon session.
Yeah. Thank you all.
Thank you, sir. Thank you so much.